And historical hydrology focused on pristine systems. And what is the reason of this choice? The reason is that we wanted to understand, and we still want to understand, how pristine system work. But now, and this is a very new development in hydrology, we are getting more concerned about human-impacted systems. Because, the study of pristine systems is not useful for our design problems. Because if we want to design, we usually refer to a system that is with humans, is not pristine. So it's important to get the connection between the humans and the hydrology and to study it, how they impact each other. Because hydrology impacts humans, of course. If you have a change in hydrology, you have a change in water resources availability and dynamics, and humans are impacted. We know that when the big rivers change their course, the ancient civilization disappeared. So hydrology impacts humans and society in a very heavy way. But on the other hand, humans are, especially in recent times, impacting hydrology in a heavy way. When you build a dam, when you promote an intensive agricultural development, you have a strong impact on hydrology. And I will show you an example in a few minutes of a natural disaster, hydrological disaster that was recently caused by humans. So, as I said, it would be better if I showed you another sketch with the humans. Here you see some numbers, some fluxes, and this is basically numbers that are given in reference to precipitation on land, which is assumed to be 100. Okay, so if you assume that precipitation on land is 100, and why this? Because the globe, on average, the global precipitation over the Earth is close to 1 meter per year. So this is why here they assume that precipitation is 100 centimeters, let's say. It's not specified the unit of measure, but this is the reason why they refer to precipitation. So if you have 100 of precipitation over the Earth, you see that over the length, sorry, the evaporation is 61, which means that evaporation is extremely important. It's 60% of rainfall. Evaporation, this is average over the globe. Or let's say, it's average over the length. Of course, it means that some water is left, so it means that we have river runoff, because if evaporation was higher than rainfall, you wouldn't have any runoff. Of course, some water is left, and in fact, if you look at the surface outflow to the oceans is about 38, which, of course, 61 plus 38 is more or less equal to 100, more or less because you have also some groundwater outflow, which is equivalent to 1 here, just to give you an idea of the importance of the water flow to the oceans from the rivers with respect to the direct flow from groundwater to the oceans. But still, it's important that you take into account that we have some groundwater flow directly into the oceans. And this kind of groundwater flow cannot be identified, defined by us. There is no way to define it. We can make an estimate like here, and we can say that it's about 1% of the rainfall, but this is just a guess. There is no way, as I said, to quantify it, and especially there is no way to say where it is more relevant and where it is less. And this is a big limitation, because this direct groundwater flow to the ocean is very important for the circulation of the streams in the ocean. It's very important. I was told this by an oceanographer who is making research on ocean circulation models. He told me, you hydrologists should give to me an estimate of the fluxes of water from groundwater to the ocean and tell me where they are. Because he said it's very important for modeling the ocean. And therefore, it's very important for modeling the climate, because you know the climate heavily depends on the ocean circulation. So the conclusion of this reasoning that I'm developing is that climate models, part of their uncertainty is due to the fact that we cannot quantify this groundwater outflow. Okay, so from the ocean you have, of course, an evaporation that is much more relevant than the evaporation over the land. And over the oceans you have an obvious result. You have also a much higher rainfall, it's about 3 times, but over the ocean you have more evaporation than rainfall. This is obvious, because as I said, the water cycle is originated by evaporation from the ocean that moves over the lands. If all the evaporation from the ocean fall directly into the ocean, then we wouldn't have any surface runoff over the lands, or let's say we will have much less, because we could count only on evaporation from land, which is not enough to trigger a river flow to the oceans. Okay, so you get an idea from here. And you see that here we have a dam which is already a sign. This is a difference with respect to the previous slide. It's a sign of the presence of humans. And keep in mind that dams are impacting the global hydrological cycle in a way that is becoming unsustainable. There are some very important big rivers over the earth that don't have any more water flow to the oceans because of dams. The Colorado River, the Yellow River, the Nile River, the flow to the ocean is reduced much. So which means that all this reasoning is heavily altered by these dams, because they categorically stop the river flow to the oceans. And where they divert this river flow, they divert it basically on the agricultural fields for irrigation, which means that evaporation from land is overexploited by humans, is increased at the expense of the river flow to the oceans. So this impact is really much significant, and it's poorly understood. Here you see some more numbers. I don't go into the details. And in this case we are talking about fluxes and storage. It's interesting to see this slide, because these are numbers that refer to real quantities, average over the earth, and they make a distinction between flux and storage, which is an important, as I said, distinction. And I don't want to spend much time on this, because basically I already put in evidence the main numbers which I'm interested in: evaporation over the ocean, total terrestrial precipitation. You see 111, and which means basically, if you look at the measure unit, these are fluxes in 10 to the power of 3 cubic kilometers per year, and basically, which it means that this 111 corresponds to 1 meter plus 11 centimeters of rainfall height over the land. And here you see, the interesting thing to see here is that we have already some indication of domestic use, industrial use, and what is interesting to see here is the dominance of irrigation. And this slide already put in evidence that irrigation plays a relevant role in water consumption, but we will talk about it later. Okay, let me now introduce some big problems that we have. And related to waters and related to water resources management. So after giving an overview of global water availability and giving an overview of the hydrological cycle, let me introduce to you the main problems that we have to solve related to water resources management and main problems that require solving this equation. I start with floods because we are not really strictly focusing on floods here. We are more focusing on droughts, water shortage, rather than water abundance. But I wanted to mention floods because they are one of the most striking problems dealing with that we have related to water. And you see here some data. Basically, floods are the most, let's say, they are the natural hazard that cause the highest damage all over the world. So floods cause more damage than earthquakes, volcano eruptions, etc. And the reason why, because you could say that floods, it's a natural hazard that is much more local and not as catastrophic, you could say, with respect to earthquakes, for instance. The earthquake is widespread and it looks more catastrophic than a flood. That's true. The problem is that floods are frequent, and if you look at the flood frequency, they are more frequent than earthquakes. And the problem is that floods are local, but they occur where people are, because people settle down close to water, close to rivers. So it's true that the earthquake is widespread, but an earthquake may also happen in an area where the population density is not as significant, and therefore it's not a big problem. The floods very frequently, I would say always, occur where people are. And this is the reason why they are a so relevant problem. And again, the mechanism that is triggering floods is poorly understood. The water balance equation is an aid to help flood dynamics. Droughts are the phenomena in which we are most interested in, because droughts are equivalent to water scarcity. And it's important to make a distinction between, because I was not correct indeed, there is a big difference between water scarcity and droughts. And according to the definition that we usually give to these terms. So what is water scarcity? Water scarcity is a permanent situation where you have a water resources availability that doesn't allow you to satisfy the water requirements from people. This is water scarcity, permanent situation, as I said. So there are countries, we know that, or islands, where we don't have enough water to feed people. This is a water scarcity situation. The drought is a temporary situation of, again, water scarcity. We could say that drought is a temporary water scarcity. And they are very different phenomena because, with water scarcity, we are much more prepared to deal with it. In principle, because if it is a permanent situation, in the past, people adapted to it. And for instance, the population didn't increase above the limit that is dictated by water resources availability. But instead, drought being an unexpected situation, a temporary and unexpected situation, we are less prepared to deal with it. Droughts are becoming a matter of concern today, an increasing matter of concern, because on the one hand, for many concurrent reasons it's becoming a matter of concern, because on one hand, water resources availability is decreasing, And here you can see the water level in an example of the water level in a well, located in the United States. And you see that the level of water in the well decreased recently. Of course, if you are overexploiting groundwater, you have a decrease of the water level in the underground. And so again, there is a matter of concern that is the decreasing availability of water resources. And also some people are concerned by climate change. So it's not just the fact that we are overexploiting it. Some people are concerned by climate change, which means reducing rainfall, etc. And on the other hand, the population is increasing, so you have an increasing water demand. So basically you have decreasing water resources availability, increasing demand, which causes, a conflict. And this is why water resources management became a science, became a subject of university courses. It was not like so until 30 years ago, as I said. And therefore, and then you have another problem, which is the water quality that is decreasing. Let's say that we are trying to recover it, but in the past, in the 20th century, in several countries over the world, we experienced a decrease in water quality. So you see that there are several factors that make drought a matter of concern. Water availability is decreasing, and I already mentioned this. Climate change, overexploitation, pollution. This is what I just said. And now this table shows you a history of recent droughts in Europe. And you don't need to learn it by memory, of course. I just want you to see that there is an increasing frequency of droughts. And I think there is another page here. And be careful when you be careful, as I said, when people report, I go back to the previous one, when people report an increase in severity of natural hazards, we always have to be very careful because, we have tremendously evolving communication means which allow us to spread the voice on events in general. And we noticed that in the past, some floods or droughts were simply not reported because people didn't care about reporting it and didn't have the opportunity of reporting it. Today, it's very easy to report whatever event because we have the web, we have the television, we have the phones. It's very easy to make events known. And therefore, we suspect that the increase in frequency of occurrence of extreme events is also due to the fact that the events are better known, which is a good thing. It's not easy to distinguish this. Also, we noticed another paradox, and this is this is funny, so I wanted to mention to you. I would like to mention to you this fact, which is, as I said, an interesting paradox, which is related to climate change. And very often we are told that the frequency of extreme meteorological events is increased. So basically, it happens quite frequently that we are shown a graph where you see time as an independent variable and some meteorological variable here. Typically it's rainfall. And then you see that the graph shows an increasing trend, like something like this. And then people fit a straight line and show you that there is a strong increase. Okay, we notice this fact that today we have more opportunity for making research and reporting events, which is nice. So basically what happens is that you observe a variable and suddenly you experience an extreme event. And when you get an extreme event, you get founding for trying to better understand what happened. And therefore people getting the founding, then they start looking at variables, at the progress of variable, and they find always that at the end of the record you have an extreme event, of course, because you got the founding for studying it. And so we noticed that in many of these studies, if you remove this extreme event, you just remove it, and you fit the same straight line by stopping here, the straight line becomes like so. So maybe a bit increasing, but not as much as in this case. This is a paradox, and it happens very frequently. We tried to collect some studies on climate change, and we said, let's remove the last 2 years in the graph and see what happens. Okay, history of drought in Europe, and here we have a sketch. I'm not sure it is legible, but yeah, I think yes. And you see, there was a big drought in Europe in 2003. You probably remember this drought. It was 10 years ago. It was very severe, and what was striking in this drought was its extension. You see the big circle. It was all over the Europe and also part of the eastern countries. It was very striking. But on the other hand, you can see that the oldest drought here is 1976. And you see a lot of them. So droughts are indeed a matter of concern. Climate change. If you look at the projections for the future climate, they invariably tell you that there will be problems. And let me say that, you know, there is an international organization which is studying the climate change, which is the IPCC, International Panel on Climate Change. They are producing reports about assessment reports on the status of climate every about 5 years. And they produced a report in 2007, and now they are releasing the subsequent one. They already released some chapters. And basically, in 2007, their prediction was much more catastrophic than now, because there was recently an increase of the global temperature. This is unquestionable. And this rise of the global temperature was very heavy from 1990 to 2004. After 2004, the global temperature seems to be stabilized. And there are many entries on the web on this. It's difficult to get information because you have too much information. But basically, if you look at the official sites of the NASA and other sites that report an estimate of the global temperature, you see that in the last 10 years the increase seems to be stabilized. And therefore the predictions that were made around 2005 are more skeptical, pessimistic with respect to the ones that were developed last year, because they realized that probably the climate is not changing so rapidly as we suspected 10 years ago. So basically there are some chapters of the last assessment report of the IPCC which are admitting that the predictions issued 10 years ago were too catastrophic. So it's not easy to show a map like this. We should say that, okay, this is a projection, and of course what you see is that you will have, when it is yellow and red, of course the situation is bad. So if you look at this situation and you couple this situation with the awareness that global temperature is increasing, you may foresee for the future a heavy migration of people from southern lands to northern lands, which would become more comfortable for people for the increase in temperature. These lands in the north, up to now, were not really attractive because it's difficult to live there. I don't know if you have the opportunity to spend some winter months in the Netherlands or in Sweden, it's very tough. But with the increasing temperature, it could be that we have a strong migration from the south to the north. This is not really something unprecedented. In the past, we had these migrations. And I mentioned to you, for instance, the big rivers that changed their course, and people migrated because people need to live where it's comfortable. The concern is that if you have a climate change in a very long time, then people have time to adapt. And this kind of adaptation is something that is natural for us. For all the living species, they adapt to a changing environment. But if the change occurs in a reduced time, then you have the wars, of course, because if you have a strong migration and in a short time, this is a reason of conflict. And look at the present situation. We already have problems between Europe and Africa with the migration that we have now. Think of a situation in 10 years from now where the migration could become 5 times higher, then of course you have social tensions and social risks. So this is a matter of concern. If the climate is changing, it's not a problem. If it changes rapidly, it's a problem. And it can change rapidly for 2 reasons, natural reasons or human reasons. It doesn't matter the effect. I mean, what matters is, if it is a human reason, you could think that we can mitigate the human effect. But it's a complicated situation, also because the predictions are not really reliable. So the future, you should always put a question mark on it. And I also would like to mention that there is a theory based on some models of the solar activity that predicts a lowering of the global temperature in the next 20 years, with a minimum in 2030. So I hope to have the opportunity to survive 20 more years to see what happens. Okay, this is a computation in the current situation of the water scarcity index, and see what is, how it is defined. And it makes reference to the renewable freshwater resources. And basically, this is computed on a time scale of a few years. And so renewable means that the water resource should be renewed continuously, not with long times. And so basically, if you put at the numerator the total water withdrawal, and you subtract the desalinated water, because of course this is something that you need to subtract, because otherwise you get an overly optimistic estimate of the situation. So for countries where water is desalinated, these are countries that experience water scarcity, so we have to subtract it. And then you divide the total water withdrawal for the amount of renewable freshwater resources, you get the water scarcity index. So you need to define a time span to compute it, and the time span usually is of the order of magnitude. For this computation I don't know, but usually is the order of magnitude of 10 years. So you get the total amount of water that is withdrew in 10 years, and the total amount of water that is renewed. Of course, if you get more water than what is renewable, you get in a situation with water stress. But the water stress is also defined when the water scarcity index is greater than 0.4. And because you have evaporation and you have losses, etc. So basically, if you look at this picture, you see in red the countries that experience water scarcity. In yellow you have moderate, because it's not depicted here on the legend. You can see it here. And so the critical situation is red, and then the yellow is not really good, and then in blue you have a good situation. And keep in mind that water scarcity can be experienced because you have a limited amount of renewable resources, but also if you have a huge amount of water withdrawal. And therefore, you unsurprisingly see that the most developed countries in the middle latitude are most of them are yellow or red, of course, because of development and huge water withdrawal. You see that Italy is yellow-red. Indeed, Italy is not in a very bad situation. We will see some details on Italy. But the south, sometimes, you know, it's a bit of, and in fact, it's red. It's a bit suffering. And let me give an idea in this slide of how much water we need. I think those of you who got in their background some courses on hydraulics and design of water supply systems already know these amounts. But please, it's much important for this course that you have these numbers clear. And this could be a question at the final exam, like how much water would you give to a town in order to make them comfortable? And you see here. So if you have 10-40 liters person per day, it's very limited amount of water. It works for very small towns. And or if you refer to the single family, it may work. Keep in mind that, for instance, the flush of the toilet is about 5 liters. And of course there are flushes now that are more efficient, but the amount on average is 5 liters. And basically for small towns, you reach better efficiency. When the size of the city, of the town increases, then you have more losses and you have less efficiency because the system becomes more complicated. But I can tell you that even if you really try to save water by all means, it's basically you need about, every day, you need at least 20 liters of water per person. And this is a very, very minimum amount. If you try to live in your house with less than 20 liters, you know, okay, you can survive 3 days maybe, but then you need more. Because if you take a shower, the shower is about 20 liters. And it's not the problem of drinking water. Drinking water, you need, like, depends on the climate, but you need from 2 to 5 liters per day per person. And if you count 5 liters to drink, and then 10 liters to take a very, very short shower, and then when you wash your hands, when you brush your teeth, if you make a computation in your normal life, I'm sure that you use about 50-60 liters per day of water, without even realizing it. Because, you know, a long shower is about 40 liters. I have some experience because I travel with a camping car with my family, and I really see that we have a tank that is 100 liters, we are 3, and then we use, usually, in 2 days the tank is exhausted, and we really try to save the water when we take the shower, really very quick shower, but it's almost impossible to survive with less than 20 liters each per day. So, if you refer to a city like Bologna, the amount of water that we use as design variables for the water supply system is 500 liters per day per person. And you may ask me, but it's so inefficient, the water supply system of Bologna. And I should tell you that this amount is a design variable that accounts also for the industrial consumption from the aqueduct. For small town, usually in Italy, we use an amount of water of 150 liters per day per person. As I said, 150 for small towns. As I said, these numbers, you should have them clear, because in water resources management are extremely important. The typical question for you is, I need to design a water supply system, how much water, I have a town with 200 people, how much water do I need? Do you have a question or not? It was just okay. Okay, so keep in mind this. and I think I can skip this. Oh, this is important indeed. And important, it's interesting. You don't need to learn by memory these numbers, but it's interesting. A question is, today, a very relevant question, is to be more efficient in producing food. And also a very relevant question is the virtual water trade among countries. So what does it mean? Because, you know, if you, in the past, of course, countries tried to be independent, and therefore they adapted their agricultural production to water availability and their food consumption to water availability. Now we have the opportunity of exportation, of exchanging goods. So basically what we do is, if a country is not able to produce internally a kind of food because it doesn't have enough water, they take the food from a country that is water rich, and through a trade of food they supply to the internal water deficiency. In doing so, countries are establishing a virtual water trade. It's like they are getting water from other countries. They get the food because it is the final product they are interested in, but it's equivalent to getting water. And therefore this originates the so-called virtual water trade. This is an emerging area of research. And so basically the question is, how much water do I need to produce one kilogram of meat, 1 kilogram of cereals? And this is interesting. It's interesting to say that cotton takes a lot of water. The gallon is about 3 liters and a half, to make it clear. I think so. If it's not 3.5, it's 4. The order of magnitude is between 3 and 4. So you see that the pound, this is a problem I don't remember. I think it's half a kilogram, but I'm not sure. And anyway, you see that cotton requires a lot of water.